Any general questions or problems? Anything? On the list of announcements, I guess, we are only 2 weeks away from Project 2. You do it in an hour, it's unlikely to be really, so please take a look at it early. If you have questions or problems, see me or see the LAs or the SI. The LAs are going to essentially use their sessions around the project being the main theme for the next couple of weeks. So do try to do your research early, especially depending on what your reaction is. It may be easier or harder to find the relevant information. And again, different subdisciplines have slightly different looking representations for kinetics. I mean, it's the same kinetics, but it's sometimes presented differently, so don't let that throw you. But if you have questions, find me before 11 p.m. on the night it's due. Any other issues? I also just moments ago inserted a bunch of slides here, so if you're following along, there's a few changes. I apologize for the last minute changes, but for consistency and approach, I thought it was better to start doing this earlier rather than later, because I have all my sayings. The more I say them, the more likely they are, hopefully, to sink in. Okay. As I promised last week, really, this week is all about what happens when you have multiple things in a beaker, because typically throwing an acid or base in water isn't the goal, right? I can throw ammonia in water, but it's usually because I'm washing the windows. I mean, Windex is ammonia in water. If I'm really doing acid-base chemistry, right, ammonia might be my base, but it is very, very unlikely that water is my acid of choice because it's a horrible acid, right? And so for the next couple weeks almost, where we're still talking about acids and bases, it's really going to be more than just a single acid in water or a single base in water. And so how to approach these mixtures of acids and bases is the theme of the week. As I'm fond of saying, of course, K is K is K is K, all equilibrium problems. That doesn't really change, right? What will change is the number of possible reactions I have, because if I have more acids and more bases, I have more possible acid-base reactions. And so one of the things I want to present, which is usually viewed as sort of a special situation, is really, I'm going to say, simply representative of my mixture problem, right? This is termed the common ion effect because in the end, there's two different sources of the same ion, right? In practice, it's really just a mixture of more than one acid, more than one base. So as a baseline, right, I remind you of our very first acid-base problem, which was the pH of good old acetic acid, right? And so if I had a 0.1 molar solution of acetic acid, in this case, the only thing I have is acetic acid and water. And so my balanced equation was acetic acid and water with a single proton transfer from the acid, acetic acid, to the base, water, which gave me acetate and hydronium, right? The K was known. If I do my ice chart, it looks very much like every acid and base ice chart we've been doing. I have an initial concentration of the acid. The change line is always just minus X, and plus X. good old I plus C is always E, and as is usually the case, I'm using my known equilibrium constant to solve for X, right? And if I did that, the assumption here you might remember works, right? My X is 1.34 times 10 to the minus 3, which gives me a pH of 2.87. Okay. And we'll come back to that in a minute, right? Because I want to change the problem slightly, because now I want acetic acid and sodium acetate in water, right? The question is the same. What is the pH? Which, if nothing else, is the hint, right, that I'm thinking acids and bases, because I really only ever ask the pH question if I'm talking about acids or bases, right? And there's my old friend acetic acid, but I now also have sodium acetate, right? Implicitly, if it's asking about pH, it's an acid-base equilibrium. If it's an equilibrium, all equilibrium problems have three parts, of which the first and most important part is balanced equation, right? But now, I don't simply have acetic acid and water. And so what the balanced equation is might not be immediately obvious. In fact, the thing that is probably most obvious, as is often the case, is not correct, right? Because, of course, as I like to refer to it, the student theory of problem solving says, well, by all means, react those two things together, right? After all, I gave you two things in a beaker. You must want them to react, right? Right? That is not how I would ever approach these, for a reason that will be clear later. And so I return you to what I claimed was one of my biggest themes of the entire semester. Ionic compounds, when dissolved in water, dissociate. Right. Now begins the part of the course where this becomes increasingly important, right? Because what that really means is, right, I don't have sodium acetate because I'm dissolved in water. Sodium acetate is ionic, right? It's a metal plus a polyatomic. It is dissolved, right? It's a 0.1 molar solution. It's aqueous, right? And so sodium acetate, an ionic compound dissolved in water, dissociates, which means, right, I technically have exactly 0 sodium acetate, right, because it dissociated, right? Even though my solution is often referred to as 0.1 molar sodium acetate, because that's how I made it up, right? I took 0.1 moles of sodium acetate and dissolved it in a liter of water, right? Fundamentally, there's an ice chart here if I wanted to create one. Right. And so what I really have is acetic acid, which is not ionic and therefore does not dissociate, right? And I have sodium ions, 0.1 molar of them, and I have acetate ions, 0.1 molar of them, right? And so, at least temporarily, it seems like my problem got worse. I had two things, which the student side of me was saying react together. I now have three things, which the student side of you is probably still saying react them all together, right? Except that sort of brings me ultimately to one of my other sayings, right? But before I get to my other saying, I actually have a fourth thing in my beaker, right? Which is water. And so I'd like to classify my four things, right? Because again, it's a pH problem. I'm talking acids and bases. What's going to matter is what my acids and bases are, right? And so technically, right, water is both an acid and a base, so it belongs in both categories. Acetic acid, of course, by name, right, is an acid. Sodium, you'll love this. We'll talk more about this later in the week. Technically, sodium ion is an acid. For now, I will let that simply settle in and blow your mind a little bit. But in the context here, it's really more of a spectator, so we'll ignore it for now, right? And acetate is also a base, right? How do I know? Frankly, the easiest way to know is it's negative, right? Anything that's negatively charged has to be at least a little basic because, of course, it's going to naturally stick to positive protons, right? More specifically, we saw it just a minute ago as the conjugate. Whoops, I copied and pasted the wrong reaction there. It's the conjugate base of acetic acid I'll fix that later. Right, and so if I ignore sodium for the moment, because it really is not an acid worth even considering, right? I actually have two acids and two bases, which brings me to my second big saying, right? What's the only thing that happens when an acid meets a base? Excellent, right? A proton gets moved from the acid to the base. Which acid, which base? All of them, right? Because again, my molecules are dumb. They run around the beaker bumping into things. You can't determine who bumps into whom, right? And so acetic acid, as it's running around, could bump into water or could bump into acetate, right? Water, when it's running around, could bump into water or acetic acid or acetate, right? And so really, I have four possible acid-base reactions, right? Every acid, and there's two of them, could react with each of the bases, and there are two of them. So there's four possible acid-base combinations, right? And technically, they're all going to happen because you can't control who bumps into whom, right? Now, in some sense, this is more work than I need to do for my particular problem here, except this general methodology, right, is really the way I want to approach all mixtures of acids and bases, right? If I have anything ionic, I dissociate it. That's just a general rule that has nothing to do with acids and bases. That's why it's my bigliest, is that a word? It's my most bigly. It's my bigliest saying of the entire semester, right? Because we do a lot of aqueous chemistry. Ionic compounds, when they're dissolve by dissociating, which means I really have the parts, not the whole, right? We've been seeing this all semester from my colligative properties with the Van't Hoff numbers, now with my acids and bases, and going forward with salts and solubility. It's a constant theme, right? And so that's my first order of business anytime I have an aqueous reaction. If there's an ionic compound, I dissociate it, right? If there's a single acid present, right, or more to the point here, if I'm talking pH and I know it's an acid-base issue, right, my second order of business is to classify all of my chemical species as either acids or bases. Because again, acids only do one thing and bases only do one thing, and you can't stop them. And so if you've got multiple acids and bases, you're going to have multiple acid-base reactions. Right? If you think about this, this really simplifies your life, even though it runs counter to what the high school student in you wants to do, right? Which is just to react everything in one big pile, right? And everything is in one big beaker, and all the reactions are really happening simultaneously, right? But all of those individual simultaneous reactions consist of a single acid bumping into a single base and transferring a single proton. So in that sense, it simplifies my life, even though you might not think so. Because instead of one big glorious reaction that really doesn't exist, because I don't have all three things simultaneously colliding in some magnificent reaction with protons flying all over the place, what I have is four separate binary reactions, right? That might seem to complicate my life, right? Because I really can't throw them out. Since they're all possible reactions, they all do happen. They're all equilibrium reactions, which means they all have to get to equilibrium, right? But as we saw last week, they aren't all equally important. Right. And so even though for the moment it might seem like my life got more complicated, it ultimately gets simpler, right? What determines who's most important? You're one step ahead of me. He said concentration of hydronium, but that's really driven by the strength of acid, which is defined by
K.
It's K, right? Ultimately, K determines who's the quote unquote stronger acid or base, and determines which one gives you the highest concentration of hydronium to get to your original point. But really what it determines is what causes the greater change in concentrations, right? Because a bigger K is going to demand that there be more products formed. Right, a small K means I don't need as many products formed, which in some cases means I don't react very much at all, right? And so this is a general rule beyond simply acids and bases, but for multiple equilibria in general, right? I'm going to do what we did last week with the polyprotics, right? I'm going to do what we did last week with the bases, where remember, ultimately I got to KW last, even though KW, is happening at the same time as any acid or base dissociation. The reason I got to it last is because it had the smallest K, and therefore it causes the smallest change in concentrations, which should not undo, right, the equilibrium I found for the earlier equilibria, right? And so again, as a general rule for any mixture, in this case, acids and bases, but it would apply to really any beaker that has multiple reactions occurring, right? Including quite possibly your biochemical reactions for your projects, right? Technically, they're all happening simultaneously, right? But the ones that end up dominating the changes that occur in concentration are the ones that have the biggest K. In the case of acids and bases, right, it's every acid with every base with a single proton transfer. If you're polyprotic, that's 2 or 3 single proton transfers. I never do more than 1 proton at a time, right? And ultimately, they technically all have to reach equilibrium, But because the path to equilibrium is dominated by the bigger changes, I solve them from biggest K to smallest K, right? And so I let K sort out which reactions I consider to be more important, right? They're all happening, they all have to get to equilibrium, but again, you're going to be dominated by the bigger Ks, and so you solve them in that order. And for these 4 reactions, 3 of them we already sort of knew, right? I mean, 2 of them we definitely knew. 1 we talked very little about last week, right? The top reaction is just the Ka of acetic acid, right? It's acetic acid reacting with water, right? We saw it just a minute ago at the very beginning when I reminded you of it, right? The Ka for that reaction is 1.8 times 10 to the minus 5. Down at the bottom, water plus water is, of course, just the Kw, which again, at room temperature is still 1 times 10 to the minus 14, right? The middle 2 reactions, right, are a little less familiar, right? We talked about the acetate as the conjugate base, right, reacting with water. That is technically a Kb reaction, and that's where, you know, I promised last week we'd see it again. My little relationship that the Ka times the Kb equals the Kw comes into play, right? Largely because I don't frequently find acetate listed on the Kb table. They assume you know it's the conjugate of acetic acid, right? But if I do that little calculation, that has a Kb of 5.6 times 10 to the minus 10. And the second one's interesting for a couple of reasons, right? It actually has the biggest K, right? If you were to actually write the equilibrium constant expression, right, it's acetic acid times acetate over acetic acid times acetate. There's only one beaker, there's only one concentration of acetic acid, and there's only one concentration of acetate. So in fact, even though technically they were in the products and the reactant side, they have to be the same concentration. It technically has a equilibrium constant of 1, right? And so if I were to rank them in order of importance by K, that has the biggest K. My Ka reaction of acetic acid has the second biggest K. As is usually the case, there's good old Kw at the back of the line with the smallest K, right? And so technically speaking, right, I need to solve all 4 of these equilibria because all 4 of them have to get to equilibrium, right? But I do what I did with the polyprotic acids. You know, there's a significant difference in K, right? The difference between the first and second reaction is a factor of 100,000. The difference between the second and the third reaction is another 100,000. And then even the third and fourth reaction has a difference of 10,000 approximately in K, right? And so my usual approach of take the biggest K first and stop calculating when things stop changing should work, right? And so if you want the brute force approach to things, start with the top reaction and work your way down. The thing about the top reaction is you could solve it, right? But it doesn't really change anything, right? I mean, if I were to set up my ice chart, you know, it's 0.1, 0.1, it's the same beaker, 0.1 and 0.1, right? You're going to end up with 0.1, 0.1, 0.1, and 0.1, right? Because the products are the same as reactants. I mean, it's not that the reaction doesn't happen, it's that it doesn't change anything, right? It's a kind of unusual situation that happens every time you have an acid and its conjugate base, or a base and its conjugate acid, right? They technically don't know they're conjugates of each other if they bump into each other, But if they exchange a proton, you wouldn't notice, at least in terms of the total concentration. If I could label them, in this case, I labeled them with red color, but I could isotopically label an acetate. And if I followed it, I would see protons jumping on and off it. But the total concentration of acetic acid and the total concentration of acetate never changes, because every time one of the acetates gets a proton, one of the acetic acids loses a proton. Right? And so even though that was technically the biggest reaction, it doesn't change anything. And so it's really not worth considering. This is one of many reasons why I say it's helpful to learn to think of acids and bases as being a pair of compounds, because it never changes anything for an acid or base to react with its conjugate, right? Which makes the first actual reaction that changes anything my old friend, the Ka of acetic acid. Right. And so I'm essentially going to start there, right? And again, I would just keep going till things change, right? I will tell you in advance, no other reaction is going to matter, right? Again, my Kw only tends to matter. We saw this with the ultra dilute sulfuric acid, right? Unless my hydronium or hydroxide is less than 10 to the minus 7, Kw generally does not contribute, and that will be the case here, right? That third reaction is actually the second reaction. I mean, it's not exactly, right? But this is the other thing about conjugates, right? And we could prove it if you want to see it. If I solve the second equilibrium, the third one has the exact same position, because it's just the same two conjugate compounds, right? Both of them really represent the equilibrium between the acetic acid and the acetate. And so if my second reaction gets to equilibrium, my third reaction gets to exactly the same equilibrium, right? And while that's a longer trip to the conclusion, again, as through the course of the week, I keep mixing acids and bases together, right? That approach is the one I want to take all the time, right? If there's anything ionic, dissociate it, right? Categorize all of my acids as acids and all of my bases as bases, and react each acid with each base, and let the Ks determine which reaction I start with, and ultimately let the solution determine which reaction I stop at, right? Like my polyprotic acids and bases, as soon as things stop changing, I stop calculating, right? If I have 10 acids and 10 bases, that is technically 100 possible acid-base reactions. I guarantee you won't have to solve all 100. That should be our next sprint synthesis. For years, I've been threatening to give that to students. I think the most I ever gave them were 3 acids and 3 bases, but it actually cleans itself up more cleanly than you might think, right? And so what ultimately is going to be the only reaction that matters is the same reaction we started with, which is acetic acid reacting with water, right? And so again, this was exactly the same problem we started the whole acid-base discussion with, except, right, I now have acetic acid, but I also have acetate, right? That was ultimately the only fundamental difference between acetic acid by itself and water way back a week or so ago, right? And this current problem, which asked me to put 0.1 molar sodium acetate in with the 0.1 molar acetic acid. All right.
I have a quick question.
Yep.
So if you react an acid with water and then it's conjugate base with water, so you're going to get a Ka and a Kb. Will those two multiplied always be Kw because they're reacting with water?
Yes. Yep. So again, my problem, as originally stated, was what's the pH of a solution that is 0.1 molar acetic acid and 0.1 molar acetate. Again, I dissociate my acetic acid because it's an ionic compound in water. And so what I have is acetate. Right. This is very common. Right. You see it in lab all the time. I don't know if you've noticed, but you know, the compounds you use in lab tend to be either sodium salts or potassium salts. And if they're sodium or potassium salts, I 99.9% guarantee you that nobody cares about the sodium or the potassium. Right? Those are just the counter ion, the spectator that brings the anion with it. On the flip side, you see a lot of nitrates. If you've got nitrates, it's not the nitrate anybody cares about, it's whatever's stuck to the nitrate. Right. And so my ice chart looks different than if I only had acetic acid, but the only real difference is I have an initial concentration of acetate. Right. I kind of sort of want to say whoop-de-doo. Right. In the end, right, it's the same methodology I always use for solving an equilibrium problem. Right. The change line is minus x plus x and plus x. I plus C equals E, and I'm going to use the equilibrium constant, which I know, to solve for X, and then I know everything. Right? And so it's still 1.8 times 10 to the minus 5. Right? Again, you know, I could solve it as a quadratic. I could plug it into good old Wolfram Alpha. I could plug it into my graphing calculator, but you know me, it's always worth trying. My simplifying assumption. And so if I assume that X is much less than 0.1, right, both of those X's that are being incrementally attached to 0.1 should be insignificant. And so I don't even have to take a square root this time, right? The 0.1s cancel, and X is 1.8 times 10 to the minus 5. Again, my standard is still the 5% rule. And so I'm much less than 5%. And so my assumption is successful. No fancier algebra required. Right. And if I put that back in my ice chart, right, again, as anticipated, the acetic acid is unchanged to at least 3 sig figs. The acetate is in fact unchanged to 3 sig figs, right? But I now have a little bit of hydronium, right? And I could prove it, but I don't feel the need at the moment, right? The third reaction is going to give you exactly 0 change in that. And because I'm significantly greater than 10 to the minus 7 in the concentration of hydronium, right? I don't feel the need to tackle Kw. And so my pH should just be the negative log of the 1.8 times 10 to the minus 5. right? In some sense, I still want to say whoop-de-doo, right? Okay, it was just another ice chart. It had slightly different initial conditions, and I got a different result, right? If I had acetic acid by itself, the pH ends up being 2.87, right? If I throw a little bit of sodium acetate in there, because I've already got acetate on the product side, I actually make less hydronium, right? Because ultimately the equilibrium constant's exactly the same. And so I end up with a higher pH value, right? This is an example of what's known as Le Chatelier's principle, which we pop into and out of every now and then, right? It's usually specifically phrased as a quote unquote system under stress responds to alleviate that stress, right? That stress can be a lot of things. One of them is temperature, which we'll talk about at some point, right? But concentrations are also stressors, because remember, the whole goal of my reaction is to balance the concentrations of the products and reactants. That means if I add anything, it's a stressor, and the equilibrium has to shift to accommodate it. If I remove anything, right, if I take my products out of the solution, the equilibrium has to shift to replace them, right? And so in this particular case, by adding acetate to my acetic acid, I essentially force the equilibrium to the left. It makes less hydronium because it's trying to compensate for the fact that it already has way more acetate than it wants, right? In this case, the Le Chatelier's aspect of it is less important than the common ion effect aspect of it, which is really in some sense the same thing. All right. Because it would be important if I had added a little bit of acetate, right? If I had a tiny bit of acetate, there will be a slight shift due to Le Chatelier's principle. What happened here was a much bigger shift, right? If you look at the ice chart, right, I have so much acetate that it looks like I had barely any reaction with the water, right? If I go to 5 sig figs, I'll see a small change, right? But there's really just way too much acetate in the system to allow the acetic acid to make more by reacting with water, right? It is Le Chatelier's principle, it is the common ion effect, but because there's so much acetate, right, this is an example of what's known as a buffer solution. I've essentially swamped my reaction with the product before I even did the reaction, right? My initial mixture had both of the conjugate species present, acetic acid and its conjugate, right? And that really limits the ability of the equilibrium reaction to do much of anything, right? And that has the useful property, right, that it limits the changes in pH. Well, we might just about have time, right? I usually, right, describe this in terms of a seesaw, because again, my equilibrium attempts to be a balance between the products and reactants, right? If you look at my normal balance when I just have acetic acid, right, the balance, that 1.8 times 10 to the minus 5 equilibrium constant, was achieved with a tiny amount, relatively speaking, of hydronium and acetate, right? There's about a 1% dissociation of the acetic acid and water, right? And so if that's my balance, right, if I throw just a little bit of acid into that mixture, it's going to swing the seesaw, right? If I add 10 to the minus 3 molar of acid, right, that essentially doubles the amount of hydronium on the right-hand side. It's a 50% increase in weight on the right-hand side, right? If you've ever played on a seesaw, right, that has to swing the seesaw, right? If it's me and 3 triplets, right, small children triplets, right? And there's 2 of them on the other end. If you throw the third one on the other end, I'm going to move, right? On the other hand, right, for my recent mixture of acetic acid and acetate, right, my equilibrium had very little hydronium, but a whole lot of acetate, with the result being that the equilibrium position, the balance of the seesaw, is largely determined by the acetic acid and the acetate. The hydronium is almost an afterthought. And so if I were to add a little bit more acid, the same 10 to the minus 3 I just did, right, it's a much smaller percentage of the total weight on the product side, right? It's a fly on the elephant's shoulder.
And which colors are rich?
What's that?
Which colors are rich with the red and yellow?
You're breaking up, or I'm breaking up.
Which colors are rich with the red and yellow?
I really cannot understand a word you're saying. Can anyone else hear him?
No.
Something about which colors are which on the scale, I think.
He posted in chat.
The yellow's the acetic acid, it's the bigger number. Size goes with concentration, right? Right, and so if I'm going to swing that seesaw, right, I have to add much more acid to do it, because I'm essentially weighted down by those 2 elephantine amounts of initial concentrations of the 2 conjugates. Right, and so where a buffer is useful is if you're trying to fix the pH of a solution against, God forbid, yet another acid or base. Right. And so buffers in general end up being mixtures of often 3 or 4 or 5 different acids or bases in practice, because to make my buffer in the first place, I frankly have to have at least 3 acids or bases. There's water in the 2 conjugates, right? But I only really want to make a buffer if I'm trying to prevent further change, which means there's at least a 4th or 5th acid or base being thrown into the mixture, right? In some sense, right, all equilibrium problems are the same. All acid-base problems are the same. I don't have to even know it's a buffer for it to buffer, right? Because it all comes out in my solution to the K equation. When I solved my K equation, and moving forward, when I solve my K equations for 4 or 5 different acids or bases, the pH ends up being whatever the pH is. All right. And part of me wants to never discuss what I'm going to discuss next because it confuses the issue, perhaps, for acids and bases which aren't buffers, right? Buffer is sort of a special case of what is just really a normal Ka or Kb reaction, right? It's just a Ka in our most recent example where I happen to have some of the product at the very beginning, right? And so in some sense, it is a special case, but because of the special case, right, there is a shorthand way to solve it, right? In general, I hate these. I mean, I've already advised you against going on the internet and finding prepackaged shorthand solutions to specific problems. The thing with buffers is they're so ubiquitous that there's almost no way to avoid this particular one. Although I would argue you never ever need to do it, right? Because it all really ends up coming down to solving the equilibrium problem, which means balanced equation, ice chart, K equation, solve, right? But because of a little mathematical magic, right, for the buffers, it is possible to pre-package the solution to the pH problem using what's known as the Henderson-Hasselbalch equation. In fact, I would argue, and I'm going to, right, this is nothing new, because the Henderson-Hasselbalch equation is really just the log of the Ka equation, right? If I take the negative log of my Ka equation, right, I'm going to get negative log of the Ka on one side, and as you may recall, we talked about it briefly last week, right? The log of a product is the sum of the logs, right? And if I do that, I get this little expression, and one of our other little factoids from last week is the negative log of anything is generally referred to as the P anything. And so negative log of hydronium is our old friend pH, right? And the negative log of the Ka is really just the pKa symbolically. And if you make that substitution, there's Henderson-Hasselbalch, right? Slightly rearranged, right? And so Henderson-Hasselbalch is really just the Ka equation, right? That said, it's not just the Ka equation for a reason I'm going to try to squeeze in the next 2 minutes, right? Ultimately, right, here's my original problem, and here's my ice chart, right? Henderson-Hasselbalch is the Ka equation, which means technically speaking, it's these concentrations. Right, the pKa is just the negative log of the Ka if we want to put a number in there. And so since the Ka is 1.8 times 10 to the minus 5, if you take the negative log of that, you get 4.74, right? And what I really have left is the somewhat unhelpful log of all my equilibrium concentrations, right? And I know if you're sitting there and have thought this through, you're like, why did you take a Ka, which was just, you know, products over reactants multiplied together and turn into a bunch of logs? We hate logs. And I would agree with you, right? This is hardly easier to solve than this was, especially because of, whoops, doesn't quite fit there. Let's do it over here. Right, even if I had to use the quadratic, at least it's the quadratic. I got a friggin' log over there, right? Except what happened when I solved my Ka equation is that the assumption worked, which meant what, right? It meant this X and this X were insignificant. Well, if this X and this X are insignificant, what do I have? What I actually have is the initial concentrations of the acid and the conjugate base, right? Henderson-Hasselbalch only works if my assumption works. The thing is, it should work for buffers because of those two big quantities on either side, right? We saw last week all kinds of examples where my assumption didn't work for just a straight acid, right? But as soon as I have that big amount of the product sitting there, I don't expect to get much dissociation, right? Because I'm weighted down by those two big initial quantities. And so my assumption, which was working 75% of the time just in general, should work 99% of the time. Right. In which case, it does really simplify my solution to the buffer problem if I recognize it's a buffer. Right. Because now my equilibrium concentration is really approximately the initial concentration, and I can just use my initial concentrations in Henderson-Hasselbeck to, God forbid, get the pH without solving the ice chart. Right? I hate this. You will just mostly love it, although part of you should hate it, right? Because again, it is a special case. And I love it in that it simplifies my life. On the other hand, it does force me to recognize a special case, and it introduces an equation which simply does not always work. If you misidentify your solution as a buffer and try to use Henderson-Hasselbeck, you'll either get a wrong answer or total nonsense, depending on what the initial conditions are, right? But where it might work, right, it saves me a whole lot of trouble. I don't, God help me, need an ice chart or a K equation because I only really need the initial concentrations, but I have to recognize it's a buffer. And we'll pick it up from there because as usual, I'm 2 minutes over. If you have questions or problems, I am still here. If not, have a great Monday as the weather gets slightly warmer. And I will see you Wednesday.
Thank you.
Thank you, Professor.